This next part of the notes discusses what's called a drift term. A drift term basically is just another parameter that's added to an ARIMA model that sometimes is needed in special cases. So to help motivate this drift term, let's take a look at something called a random walk model. And what a random walk model is simply is an ARIMA 0-1-0 model. So of course then that means that the D for differencing is equal to 1, but we have no AR or MA terms to our model, or parameters to our model. And so this is what the model would look like, simply 1 minus B times X of T is equal to WT. Or we could rewrite it as XT is equal to XT minus 1 plus WT, where WT is distributed independent mean zero variance sigma squared W. Now where the name random walk comes from is as follows. Basically imagine, let's say you are starting at a place at a numerical value at time t minus 1. Now to get to time t, you just add a random value coming from a particular distribution as mean 0 and variance sigma squared W. So in other words, you are moving in a random direction from where you were at time t minus 1 to get to time t. Thus, in other words, you can think of it as it's a random walk. You are randomly walking in a variety of different directions depending upon what that random variable WT is observed to be. This random walk model occurs in a number of different places in actual application. For example, in financial time series, like with respect to, let's say, the stock market, due to, in finance, what's called an efficient market hypothesis, basically a random walk model can be used in that kind of a setting. Okay, so this is what then is sometimes needed when you have a situation like this. Rather than just having that plain model, that ARIMA 0-1-0 model, an extra term called a drift term is added. This delta is the drift term, and it is actually a parameter that you will want to estimate. And so what this is saying now is that to get to time t, you start at what your value is for time t minus 1, you add that random component, but you also add an additional value to all this. Now to understand the effect then of this random drift term, and also will help you see why it's called a drift term, let's take a look at x of t in terms of a cumulative sum. Meaning, okay, let me do a little bit of erasing here. If x of t is equal to delta plus x of t minus 1 plus wt, that means then, of course, then x of t minus 1 is equal to delta plus x of t minus 2 plus wt minus 1. So in other words, let's stick this in to there. And that's what I do right here. Do a little bit of algebra, simplify, and now notice I have 2 times delta plus x of t minus 2 plus wt minus 1 plus wt. Of course, then that means x of t minus 2 is equal to delta plus xt minus 3 plus wt minus 2. So let's stick now that in for x of t minus 2. And through a little bit more simplification, look what I get here. I get 3 times delta plus x of t minus 3 plus wt minus 2 plus wt minus 1 plus wt. And you could keep on going and going and going. And eventually you'll see that x of t is equal to delta times your time t. So this is a numerical value like 1, 2, 3, and so on, plus a sum of your deltas. I'm sorry, a sum of your w's. And so, at least in a numerical context, we can think of now why delta is a random drift term. What's going to happen is as t increases, is going to cause that random walk that we had previously seen to keep on moving in one direction. It's going to move, let's say, up or increasing if delta is positive. It's going to go down if delta is negative. So in other words, this is a non-stochastic trend in the series because t is just our time index, delta is a parameter. There is no random value there. And so, again, it allows x of t to drift away from 0, which is what it would have been previously with a plain old random walk model. Now, what this is also going to mean is that, if I were to take the expected value of x of t in this situation, it's going to be delta t plus the expected value of the sum of these w's. This sum, oops, it should be delta times t. This sum is going to be 0, or the expected value of that sum is going to be 0. And so we can see that now we have non-stationarity in the mean. Previously, from our discussions, we know if I take these first differences with respect to the mean, if I had a linear trend, that would remove any kind of non-stationarity in the mean problem. Well, very often that works. But if there is this random drift component, then that will not work. And so by including this random drift term in the model allows you to account for that. Okay, so how can we then estimate what delta is? It's a little bit more complicated than what you might expect. So with the ARIMA function, we of course can use that with differencing by using the order argument and the correct values for the order argument. We have an include.mean argument as well that allows us to estimate mu. And we saw how mu was just kind of this extra part to our ARIMA model if we can't assume that x of t has a mean of 0. Obviously, with a random drift case, we don't have a mean that's equal to 0. So maybe you might think, well, could we just somehow have include.mean equal true in there and somehow get at that random drift term? And the answer is actually no, we can't. That's because with the ARIMA function, whenever there's differencing, include.mean, that argument is always set to false, automatically by R. So even if you put include.mean equal true in your ARIMA call, R will automatically set that equal to false. And the reason being is because differencing is supposed to remove trend and allows for the different series to have a mean of 0. This is what we've previously seen. So despite what the ARIMA function allows us to do, there are times where we still would like to estimate this extra term to our model even when there's differencing. We'll look at ways to get around how ARIMA is set up so that we can still estimate that delta. For now, though, let's take a look at what our full ARIMA model could look like with that drift term. So here's our ARIMA model. We have this AR component. We have the differencing as well, times x of t. That's set equal to the random drift term plus the moving average operator times WT. Now, most time series books, and in fact when I even took a time series class when I was in graduate school, they often don't even talk about this delta, the possibility that it can occur. They don't talk about how to estimate it. So for example, one of the main books that I used when I was in graduate school, and there's been subsequent editions released since then, is this book by Way. And this is what Way's book says about the possibility of a random drift term. We assume that theta 0 is equal to 0, where theta 0 is their version of delta, unless it is clear from the data or the nature of the problem that a deterministic non-stochastic trend is really needed. And that's basically all they say about it, or that he says about it in his book. Never really comes back to it. And so that kind of gives you some reasoning behind why, R doesn't make, let's say, estimating this delta really easy. So how can we then go about doing this? How can we go about estimating delta when needed? Well, we can use the XReg argument inside of ARIMA. We've seen an example of using XReg in the past, and we're going to use it in a similar manner, but slightly differently. With the XReg argument, you can say 1 colon the length of x, where x is your time series. And that will allow you to now estimate this drift term. Well, 1 colon length of x basically corresponds to 1, 2, down to n. So essentially you're going to add an additional term to your model, basically like t. And then you're going to estimate the corresponding delta for that. So this kind of gets it back at what we saw previously when we rewrote the model so that we had that delta t in there. Now another way to go ahead and estimate this random drift term is to use some functions from the ASTSA package. This is a package that was written specifically for the Shumway and Stouffer book. And if one used the ARIMA function in that package, where S stands for seasonal, rather than, let's say, Shumway and Stouffer, one can go ahead and specify a particular argument in the ARIMA function to actually estimate that drift term. The reason why we have an S for ARIMA, an S for seasonal, is because a little bit of a general way to look at ARIMA models is to include a seasonal aspect. Let's say maybe you have data that's observed for month by month, or by actual, let's say, seasons, as in spring, summer, fall, and winter. There are ways to specify that effect in a particular model, and we will actually look at that a little bit later in this course. And lastly, what one could do is actually do all the differencing that would be needed before you actually invoke ARIMA. So let's say your data is in X itself. Use the diff function with that and with the appropriate differencing that you need in terms of the arguments. Put that into an argument Y, and now use the ARIMA function itself and estimate the model with a d equals 0. This then will allow you then to do some, allow you to estimate the drift term. So let's take a look at some examples of how to actually estimate the drift term with some data. So this goes back to our ARIMA 111 example. While this isn't a random walk model, basically I chose this particular example to show you that indeed you can estimate the drift term at any point whenever you have a d that's equal, that's not equal to 0. You could still estimate when you have an AR component, when you have an MA component. Okay, so now this data was actually simulated from an ARIMA 111 without a drift term. So in actuality, in this particular case, the true value of delta should be equal to 0. Let's see what happens. Let's see if we actually come up with that when we estimate it. Okay, so to begin here, I'm going to simply read in my data like usual, put it into X, estimate the model like usual. Here is my phi hat 1, here's my theta hat 1. Here is sigma hat squared W. Then I can also do my forecasting like usual. I can use the predict function with that. I'm going to go 5 time points ahead into the future. And so this is what the actual estimated model looks like. Okay, so to implement the first method to estimate the drift term, I'm going to use the ARIMA function with the xreg argument 1 colon to the length of x, 1 to n. And here's what I get. I'm going to put the results into mod.fit2, for the lack of a better name to say the results in. Use the ARIMA function, and here is that xreg argument. So we get different values of phi hat 1 and theta hat 1. That's not surprising. We are actually estimating a different model, so don't be alarmed by that. And then here's where we get the drift term. So here is delta hat, and here is the estimated variance of delta hat, actually the square root of that. Here is sigma squared, sigma hat squared W. Okay. So there's my corresponding parameters, or parameter estimates. If I want to do forecasting, I do it exactly the same way as before, but now I have an additional argument here. I have new xreg here. And what this is telling R now is that for time points, I have a n equal 200 here. I need to tell R, well, what should happen at t equal 201 to 205 if I want to go 5 points ahead. What should be the corresponding value in this case for t? And so what I tell R is that I want to start at the length of x plus 1, in other words n plus 1, and go in terms of the integers by 1 to n plus 5. Here are the corresponding then point estimates for these forecasts. Also, what I can do, and let me come back up here, perhaps I should have done this before. If I want to, I can do inference corresponding to delta. You know, if I wanted to do the hypothesis test of delta equals 0 versus delta not equals 0, I could form a walled test, and I would get negative 1.6847 divided by 0.881. That looks like a 5 there. I get my wall statistic, which is, and I actually went through the process here. I actually pulled it out of the COIF component of the return lists. I also pull out then the estimated variance from the return list, and I get negative 1.91 for that ratio. This obviously is close to, let's say, a negative 1.96 if I, let's say, use alpha 0.05 for my hypothesis test. So what this is saying, and perhaps surprisingly, is that I have marginal evidence that a drift term is needed. Now, again, remember, delta was truly equal to 0 when I simulated the data. So to some respect, this one could say that maybe this is somewhat like a type 1 error that we're actually witnessing here. Okay, so here's what my model looks like then, using all the components that I had from the ARIMA output. Here's my delta hat that would be put into the model. So that's method number 1. So method number 2 is to use Shumway and Stouffer's ASTSA package. Now, this will give us almost an automated way to actually, let's say, estimate then this this drift term. And you might be wondering, well, why don't I just simply always use this package itself to do the estimation? And generally, My, I guess, rule of thumb when I use R is I always try to use the functions that are inside the default installation of R first, and only use functions from another package that's user contributed only when there's a significant improvement given by those corresponding functions relative to what I have normally in R. And part of the reason why I do that, and there's actually more than one reason, but part of the reason is that, let's say Shumway and Stouffer's book goes out of print, and they decide they're no longer going to update their package. Well, their package can then become archived, meaning that it's no longer easily downloadable anymore because the package is no longer being updated to the current standards of R. And so, therefore, it makes it a lot more difficult then, and maybe even impossible, to take advantage of this, when otherwise, like the ARIMA function that's already in R will essentially always be there. Okay, so enough about that. So I install my package like how I would normally, and then to actually estimate the model, I use their ARIMA function. Their first argument, x data, corresponds to where my data is, and I have separate arguments for p, d, and q. So I go ahead then and print off the results from mod.fit.ss. Now note that the way that this function works, it basically uses the ARIMA function that is in the regular old stats package in R and does some small modifications to it. And that's why you see ARIMA actually listed right there. And in its output, here is delta hat, exactly like what we had before. There's a number of other useful things here. For example, here's the corresponding p-value when I would test is delta equal to 0 or not. Now, whenever you do run this function, please note that you also get some plots with it. These plots are often referred to as diagnostic plots, corresponding to, or the purpose is to check if the corresponding assumptions, mathematical assumptions with our model, are they satisfied or not. We'll be talking about these diagnostic measures in a separate set of notes, so I'm going to skip over looking at these plots here. And one could also use their ARIMA.for function to do the forecasting, and it works much the same way as what we've done with the predict function itself. Here we don't need to specify new xreg because it can automatically detect that, okay, you are estimating this extra term. The function from Shumway and Stouffer's package also automatically produces a plot of the forecast too. And what we actually have here is in red are the actual forecasts. These lighter gray lines are basically the corresponding confidence intervals, like what we've calculated before. Approximately 95%, but not quite. Rather than using 1.96, it uses plus or minus 2 for the corresponding quantiles used in that interval. And for some reason also it actually goes uses a plus or minus 1 rather than the standard normal quantile as well. And lastly, excuse me, the last method that one could use is, as I mentioned before, use the ARIMA function with the differencing already done. Specify d equals 0 in it because you've already done the differencing before, and also have include.mean equal true as an argument with inside of ARIMA. You can see my corresponding program for its actual implementation. But do note, I think methods 1 and 2 are a little bit easier, and a main reason behind that is because eventually when you want to do forecasting, like with the predict function, what you're actually getting forecast for are, let's say, y sub t is equal to 1 minus b raised to the d power times x of t. That's what you're getting forecast for if you use this third method here, rather than getting x of t itself. So because of that, then you're going to need to do the integrating to get back to the x of t scale to have the forecast and the actual numerical scale that you would want rather than the difference scale. Okay, so that concludes then this small section on drift terms.